Delayed conduction. Why do we use it? Okay, so you've got to think in terms of bucking coils. We've got two output coils, partnered output coils. Partnered output coils are used all over the show. They're bucking coils, basically. You'll see them in common mode chokes. You see them everywhere, and they are typically designed to stop transient. Now, this is something that is quite unique, actually. What we're doing is we're actually causing transients, if you like, if you want to put it that way. Delayed conduction is basically one coil conducts, carries a current, and this is the important part. And then all of a sudden, a split second later, the other coil will conduct and then carry a current. Now, when both coils conduct, they hold the current steady, and each coil the current in each coil is equal and opposite. It has to be due to Lenz's law. Lenz's law states that the change in the magnetic field must be equal and opposite to the change in the source. So it's always going to be opposite. It's going to be bucking. Delay conduction. There's lots of different ways that delay conduction can be done. For example, Terrell Caponese, he uses a spike, a spark gap with a spike on top of an AC wave. Typically, at least in my investigations, his AC wave was 50 Hertz. He uses a spike on the top of the 50 Hertz, and that spike essentially sends the coils into if you like, a unbalanced conductive state. Graham Gunderson did a fantastic job of his demonstration at the 2016 conference. Showed a lot of information and showed a machine that was at least 5 times above the input. Some people have disputed the measurements and all that sort of thing, but you've got to remember that Graham Gunderson is highly trained engineer. He's been doing this for decades. He did measurements that I cannot fault. I am no expert, but from what I've learned, I cannot fault his measurements. His measurements were absolutely 100% spot on. Those other people that have questioned his measurements have picked on some things that are just so silly, it's just not funny. I mean, honestly. Anyway, moving on. Graham showed an inductive spike, and this is the spike here, you can see. Now, this is a very important waveform. This purple line at the bottom is when the partnered output coil on the left is connected to the load. Okay, the gap in the middle, where you see here where it's actually spiking, is where the partnered output coil is disconnected, and again reconnected down here. So this is connected state. Now this connected state, there's a few things here I'm not going to go into yet, but this connected state here is where you see the waveform here. So this spike, okay, the spike on this side, and then the spike on this side. Now what this spike actually is, this is an output current. So this green waveform here, this output current is actually completely flipping in polarity. Okay, so it's going from positive up here, where this arrow points to negative down here within a split second. Okay, it's very, very fast. It's a very fast spike. And the distance between the connections, this spike here and this spike here, is equivalent to the distance between here and here. The time base on the scope down the bottom there, m equals 4 microseconds, m equals 4 microseconds. So that it's the same time base, it's the same spike. Okay, the area in which the switching, the output switching, or the output conductive delay is happening, the area this is happening is approximately at the power, at the actual power level in this particular unit. You've got to remember, Graham's input is an LC tank circuit. It's in resonance. His voltage here is leading the current here, which is in blue, and it's by 90 degrees. So the peak of the, well, roughly 90 degrees, the peak of the voltage is approximately equal to the zero cross of the current on the blue. Okay, so the area that Graham is switching is in the power area, where power is being delivered to the machine. Okay, this is a delivery side of power. So at this particular point where the switching is being done, there's a high energy state that's been brought into the machine, and at this particular state, all the coils in the machine are exposed to a higher energy level than what they would be if it was all zero. So for example, if there was no input waveform, the energy level that the coils would be exposed to would be zero, obviously, because there's no input energy waveform or anything there. It's a pressure. You've got to think of it as a pressure. Terry Caponese did the same. All the machines are all the same. The conductive, or the copper, has got to be exposed to a high energy field initially. Now, in my opinion, from my research, what it does is it brings the copper atoms up into a higher energy state and allows for more copper atoms, or at least electrons, to be freed from the binding states inside the copper atom themselves. You've got to remember, copper is conductive. Charge flows through, or at least on the outside of the copper conductor, and the insulation itself is a barrier where the copper, or at least the charge, cannot pass. So say, for example, if we had a generator, okay, our generator had really nice terminals coming out, but the insulation wasn't peeled off the terminals, and we tried to connect our light to it, we'd get no light. There'd be no light because the insulation on the terminals would stop us from connecting to the copper conduction. And no matter how fast we spun our generator, we would get no light. If you bare the ends, take the insulation off the coils, and then connect your light, then the light will glow. So you've got to remember that conduction is extremely important. Conduction is one of the most important things, and we so take it for granted it's just not funny. Anyway, the copper conduction, or the copper atoms, are exposed to a higher energy state than what they normally would be, and the higher the energy state, it seems to we seem to be better off. At least that's in my experiments. I have only gone to certain levels of energy. I don't use very much. I try to keep my input power levels to a minimum. Obviously, I don't want to use too much to get a reasonable output. Now, it's very important. I recommend, I've said it before in the forum, start small, start simple, and start with very low input. Because sometimes these machines, they can give you spikes that you really don't expect, and they can be very, very damaging. So be careful, don't hurt yourself, don't damage your equipment, be careful. This is one post I just wanted to run over. This is an image that Graham showed in his conference lectures. Again, shared thanks very much to Ryuki. The purple trace is the one that's selected at the moment. The zero gradical line is up here. This is 9 volts negative down here. The yellow is the input voltage, blue is the input current, and green is the output current. Now this is, again, this is set to 4 microseconds. You can see the spikes in here. Okay, and where these spikes are, again, I just wanted to reiterate, this is where you see these spikes here. Now Graham has switched over at this stage to a high voltage probe, okay, and the same channel, channel 3, and it's purple. So this is showing the same voltages up here, same channel, but on a different probe. So this probe here is a high voltage probe. The zero gradical line here, 9 volts is being shown, and it doesn't really look like much at all there. So this is connection, this is conductivity connected through to the output. The red markers indicate an off time. Again, we're looking off time at the same points. Conductivity again. The spike here is being indicated by the blue line that I put on, which is around about the 700 volt mark. Slightly lower, but around about 700 volts. Again, the time base on the scope, 4 microseconds. Okay, and if you scroll in, this is where you're back on the low voltage probe again. This is the flip in polarity in the current on the output current, and you can see here again, this is the there's a double wave in there. Okay, now I think it's very important to actually see these things and try and sort of understand them for what they are. Basically, what we're seeing here is this flip in current. It's flipping the same way every single time. There was no inconsistencies with the flip in Graham's demonstration, and that is due to this switching here. And this is a double switching. So this is disconnect one coil, and then at the end of the disconnect, obviously it reconnects again. At the start of the first coil's reconnect, then the second coil is disconnected. Okay, and what happens here is between this disconnect here and then the reconnect, and then the reconnect to the disconnect, this time in here, these two coils are slapping together very hard, very fast. Okay, you've got to remember that these coils are very low resistance. The inductive reactance and the overall impedance is very, very low. And obviously, if you take into account the reduced impedance, in fact, that I've been showing, then it will almost be zero, if not zero itself. So there'll be almost no impedance in there by the time that this happens. So you've got to remember that maximum current can flow through these coils at any one time, at least during this part of the cycle where they're actually slapping together. And you can see that. You can see that by the very, very fast flip in polarity in the current between the top of the peak and the bottom of the peak down there. Okay, the timing that we can see here and that we've seen on the output current waveform where it flips polarity very, very fast is related to this image here. This image here has been tied to the input on the other forums, and some people are telling you that this is the input timing. It's not. It's absolutely not. Anyone that knows anything about H-bridges know that this is not going to give you the waveforms that we've seen from an H-bridge. It's just not. Anyway, it is tied to the output, and we've seen that here. We've got proof of that here. We can see it in the wave here. Now this image and lots of other images were very kindly shared by Ryuki, and I want to throw a big thanks out to Ryuki. Ryuki went to the conference and pestered Graham afterwards for lots of extra information and diagrams and bits and pieces like that. So thanks, Ryuki. Great job. Thank you. Anyway, PWM-A seen here, PWM-B seen here, and these two waveforms are linked to each other. And you've got to remember this is either inverted or how it is, depending on where you're measuring it from. We know for a fact that the conduction between the cycles, was from here to there on PWM-A on the coil on the left-hand side. And then the other side obviously was slightly after that. So what's happening here is PWM-A is switching the MOSFET off for a very, very, very short time. And then after it's switched off, it reconnects again. Okay? So you've got to think that the very short period of the cycle is off time. And then the rest of the period is on time. And the same goes here for PWM-B. So very short period, is off time on the MOSFET, when the MOSFET's off, and the rest of the period through here is on time. Okay. Now, what happens is when these two coils are switched in this fashion, when one is conducting, if you like, which is at this point here, it's at the end of the off time, it's conducting, so it's starting to carry current, and then the other one is switched off for a short period in time. So current's going to build, and then all of a sudden it gets to here, and this coil starts to conduct, and then all of a sudden the coils are going to slap together very, very hard. There's going to be Lenz's law, which is going to push these coils to the absolute maximum of their capabilities. And that's when we see the big wave that I've been trying to show for some time. The big wave is when the coils slap together very, very hard.
Nature is so dramatic, isn't it? Very dramatic. Wow. Wow. Like symphony.
Okay, so the coils slap together very, very hard, and that's what creates this spike. Okay, the spike is much, much, much greater than anything else in the system. 700 volts is well in excess, nearly by 100 volts of the input. The input, I think from memory, was around about the 600 volt region. Now, obviously because it's 90 degrees out of phase from the voltage and current, it's a resonant system, so power is being transferred back and forth from the inductor and the capacitors, so very little input energy is actually being used. Input energy is not being used at all if it's at 90 degrees. Everything that's transferred out gets returned back again. Okay, and when a tank circuit like this, consisting of a capacitor and an inductor, and when the arrangement is excited with a voltage source that is at the right frequency, the frequency of the oscillations just go backwards and forwards. And when this happens, we see an effect on the scope, or at least on the plot, like this. So voltage is sinusoidal, current is sinusoidal, and normally you would see something pretty close to sort of 90 degrees. 90 degrees is a bit unrealistic in most cases. It might be 83 or 87 or something like that, depending on your arrangement. Anyway, the power that is delivered and returned from the machine is signified by the purple line here. Power is not consumed as such in this case. This is wrong. It should be power delivered, power returned. Okay, you can't return any power if the power is consumed. Okay, if the power is consumed, it's gone and you can't use it anymore, which would indicate a resistive load and it's burned it up as heat or something like that. But in a capacitor inductor arrangement, if it's set up to be very, very efficient, the power returned is normally just a little bit less than the power delivered. So there's always some losses. If there's too much resistance in the coil or something, or too little resistance in the coil, the resistance might burn a little bit of heat as power. So power is burnt as heat. Okay, so this is something that we've covered before and should be pretty sort of well known. This is the x-axis here, which is time. Time is t. Y-axis on this scale over here, which is the amplitudes of the waves. And again, if your voltage and current are 90 degrees from each other, your power delivered and your power returned is exactly the same. You effectively use no power if it's 90 degrees. There is no power lost or consumed if it's 90 degrees. All power delivered is the same as the power returned. I just want to point out that Graham Gunderson's method is not the only way to do this. This is a method of switching that can be done various other ways. For example, I've shown a way with an H-bridge, which is that particular experiment achieved the end result, but wasn't completely successful. And what I mean by that is the output power was not greater than the input power, but the experiment proved a point, and I've shown that on the forum. Obviously, the goal at the end of the day is to find where the waves slap together the hardest, and it does take a little bit of tuning. There's a little bit of tuning that's required. For example, if your first coil conducts, starts carrying a current, and then your second coil starts conducting, a minute or so later, it's probably not going to work. This seems to work very quickly. There's a very short time frame in which the coils slap together and create this effect. This effect will give you a triangle wave. I've pointed that out on the forum already as well. You will see a triangle wave. Some people say it's there, but they're still not getting extra output, and that is possible. You've got to work to try and achieve the best result. So it's a little bit of fiddling. So what you have to do is you have to look for these effects that we're trying to show. The MEG team use a similar method, which is much simpler, and obviously there's not the complex circuitry or microcontrollers or whatever required, but they achieve the same end result, and that's a delayed conduction. They use what's called a TVS. A TVS is a transient voltage suppressor, and what that is basically is a xenodiode with a diode. So the xenodiode stops the conduction up until a certain voltage, which might be 10 volts, 18 volts, 120 volts, or even 200 volts or more. And then at that particular voltage, it then conducts and then obviously dumps the voltage to ground. And the image that you're seeing there is an example of that.
Now we'll review data plots that show the kind of performance that we can expect from the system in its operation. Again, the data displayed is for the side A input coil top and the side A output coil on the bottom. Side B is a mirror image of the data shown. Because the nanocrystalline material responds rapidly, we were able to run the system at 31 kilohertz. The material doesn't absorb significant energy and does not heat. We couldn't directly connect a load to the input coils that we were not activating. However, we were able to place a device called a transorber across the coil. This allowed us to measure part of the power available in this coil. If we sum the output for both sets of coils and include the power from the input coils that were not energized, we have about 2 times the amount of power out that was used on the input coils.
And here's just a JLN. This is one of the early JLN ones from, I believe it was about 2000. Yeah, December 10th, 2000. Here's MEG. Here, obviously input coil, input coil, magnet in between, obviously wires to the input coils. This coil here is wired out to, in this case it's just a resistor, JLN did some strange stuff with a resistor. Basically, fired a whole bunch of high voltage through it to stop it conducting up until a certain voltage. Now, he did use MOV and MOV. It's in the same family anyway. So basically, this side will conduct at a certain voltage. This side's conductive all the time, and once a certain current is reached on this side, obviously the voltage increases on this side, and then that causes the peak. And you can see here at the top, you can see the peaks go all crazy. Now, what the MEG team did show, which increased my opinion, they did show enough information here to actually correlate some of the other machines as well. So obviously the key here is the triangle wave that they show. Up the top here is the input. So these very short from here to here sort of thing is the input. That's not a very good example. This one here is a better example. So input shoots up, and then is switched off. And then at this stage, if you follow this down, right down at the peak down here, this time in here that you see is time that it builds. So this is a building stage here, and you can see the input is switched in here, and then all of a sudden there's a conduction. So the conduction is fired either there, or depending on which way you want to view it, up here. Now, I believe this plot is it's either plotted with the time axis inverted or the y-axis inverted. There's something wrong with this plot. It's not what you should see exactly, at least anyway. The idea is there, but it's not what you should see. Here it is, a metal oxide varistor, a MOV. That's what JLN used, and he said it was critical. And again, the MOVs, they conduct at a certain voltage. They are rated to a certain voltage. The TVS is basically the same machine. There's a bidirectional one where there's two, or a unidirectional one. So take your pick. So the idea is to get the coils conducting at a certain time relative to the voltage that they're carrying, and to try and do it as quickly as possible. There's obviously is a resonance to this. You've got to find a frequency where it suits. So up here and down here is current. So this is the current that say for example in this case the coil would be conducting, which at this stage is 0. As you move up in voltage, the current slowly moves up, as you can see. So all the way up here, obviously it's nearly at full conduction. So the MOV or the TVS or whatever you want to use would be full conduction up around the voltage that's been specified. Now, forgive me, I can't remember off the top of my head what these are. They are named BR, WM, and C. This is the voltage, and it's to do with the region of conduction at the time. VC, voltage conduction, I believe might be the case, but have a look at the data sheet anyway. Now you'll see this particular plot that is of, I believe, the TVS. Yeah, the TVS. This one here, this is a plot of the MOV. So the MOV and the TVS are very, very similar. You can see there's a certain voltage that you've got a forward voltage that you've got to reach before conduction starts happening. And like I showed previously, obviously the timing of the waves slapping together gives you this end result. Now the waves, the voltage might be in one direction, but obviously the current's going to be in the opposite direction. So look for that when you're doing it. This is just a quick picture of a MOV. They just look like diodes, but again, they will conduct at a certain voltage, so they're not a diode as such. But yeah, very interesting little devices. So TVS, the MEG team refer to it as a transorber, and a MOV, a transorber and a TVS. It's a little bit hard to explain, but Transorb is a company, so it's a company name, and they produce the TVSs. So that's why some people refer to a TVS as a transorber.